I have started talking about the importance of secondary refining. In the last 2 or 3 sessions, I have already covered some of them. Initially, I talked about the limitation of primary, why secondary refining is necessary, then what are the common secondary refining processes, and some of them I had discussed, what are the requirements and how different steel making process they are fulfilled. Then I have talked about in details about deoxidation, what are the issues, which element we can theoretically know is a good deoxidizer, which one is a relatively moderate and which one is a relatively less deoxidizer. So, what are the deoxidation stages, like you require the inclusions to float up for decreasing the alumina or silica, whatever inclusions have formed. Then I have talked about an important issue like to prevent reoxidation and phosphorus reversion in liquid steel, carryover of slag from primary furnace towards end of tapping has to be restricted. Why I talked about this? Because primary slag has very large amount of iron oxide. It may be about, it is much more than 20%, maybe 25%. Moreover, it has some amount of MnO, manganese oxide. It has some amount of phosphorus oxide, which by the way phosphorus has got transferred in primary steel making from metal to slag in the form of phosphorus oxide. So, if this carryover slag, that means primary furnace slag, when if it is carried over to the ladle to during subsequent secondary refining stages, this will create problem. This will have implications on the quality. Iron oxide might react with aluminum in steel, generating alumina. Phosphorus oxide might react with aluminum in steel. So, there is a chances of phosphorus reversal. MnO, if it which is there in the primary slag, when it is coming to secondary stage, if it comes, it will also react with aluminum in liquid steel, generating manganese oxide. So, in the process what is happening is reoxidation is happening. That means, the aluminum which is present in liquid steel is getting oxidized to alumina, and phosphorus oxide which was in the slag. So, there is it will react with aluminum and there is a possibility of phosphorus reversion in liquid steel. So, these are implications on quality. And moreover, if this aluminum by the process of deoxidation, aluminum which is present in liquid steel, dissolved aluminum, it comes down through reaction with iron oxide or phosphorus oxide or manganese oxide, then what is going to happen? The dissolved oxygen in liquid steel also will come down, because dissolved aluminum is increasing, or just the reverse, dissolved aluminum is decreasing by this reaction. So, dissolved oxygen in liquid steel is going to increase, which has a lot of implication on the quality. So, effective slag stopper I had told is very important. Moreover, I had told you that basic slag and basic refractory, why these are important? Because basic slag will be helpful in absorbing the inclusions which are floating up, whether it is alumina or SiO2. And basic refractory lining is important, because if you have less basic refractory lining, that means if there is SiO2 in the lining, some amount of SiO2 as as undesirable constituent in the refractory lining, it will react with aluminum in liquid steel and generate alumina, which has to be taken care of. Dissolved aluminum will come down. So, reoxidation is a problem. Now, flotation of this aluminum oxide I have talked about, Stokes law, how does it help, how does it rather explain why inclusions which are larger in size should float up at a higher velocity, because the density of the inclusions are less, and smaller inclusions they will coagulate to form larger inclusions. Fortunately, larger inclusions are floating up at a higher velocity, So, they will float up and get absorbed by the at the basic slag. Then I have talked about desulfurization, and I have mentioned how CaO in slag is very important. So, we must have about 50% CaO in the slag in the secondary refining processes, and the basicity, that means the ratio of CaO and SiO2 in the slag should be at least 3, it should be preferably more than 3. So, I have explained why more CO is useful and less oxygen in liquid slag is important. You will see here, the sulphide capacity is proportional to the weight of CaO in the slag and inversely proportional to oxygen content in liquid steel. So, oxygen content in liquid steel, that means the dissolved oxygen in liquid steel has to be low to get a good amount of desulfurization. That is why I have mentioned earlier, and again I am repeating, good deoxidation is a prerequisite, is a necessity for getting good desulfurization. Then I have talked about the importance of degassing, how hydrogen and nitrogen, which are gaseous elements present in liquid steel, how they can be removed by degassing. This hydrogen present in atomic form in liquid steel, nitrogen present in atomic form as soluble nitrogen in liquid steel, they get transferred to the surface of the steel gas surface, and in that process the hydrogen gas or nitrogen gas is taken out. So, the partial pressure of hydrogen or partial pressure of nitrogen is going to play an important role. Lower the partial pressure, better will be the degassing. So, lower will be the this H, small is the Henryan activity of H and nitrogen. That means, hydrogen and nitrogen activity and likewise the content in liquid steel will go down if I can maintain lower partial pressure of hydrogen or nitrogen. So, this is the way vacuum helps. Vacuum reduces the partial pressure of whatever gases are present, and in the process this gaseous elements in liquid steel can be brought down, and it can be shown that at about 1600 degrees centigrade and at normal atmospheric pressure, the hydrogen and nitrogen limits are about 5 ppm and 50 ppm, but at about 1 millimeter mercury, which is called 1 torr, it can be calculated from these relationships that hydrogen can be brought down to 1 ppm, nitrogen theoretically be brought down to 15 ppm, but I had mentioned that what is the difficulty in degassing of nitrogen. I have mentioned whatever I have told you in the earlier slide, that is the theoretical considerations, thermodynamics, but if you look into the kinetics, which is associated with thermodynamics, that means in reality kinetics will play a very important role. Now, if you look into how nitrogen is getting transferred, first the dissolved nitrogen which is present in liquid steel has to be transferred from the bulk of the steel to the surface of the liquid steel, then only it is possible to get transferred. Then at the surface this chemical reaction will take place between atomic nitrogen to gaseous hydrogen, or atomic nitrogen to gaseous nitrogen, or atomic hydrogen to gaseous hydrogen. So, first the mass transfer of nitrogen in liquid steel, then the reaction, surface reaction from atomic to molecular or gaseous hydrogen and nitrogen, and then this gaseous nitrogen and hydrogen, it has to again get transferred in the gaseous phase. If it remains at the interface, the reaction is hindered. Now, all these 3 steps, mass transfer of nitrogen in liquid steel, slow surface chemical reaction, and mass transfer of nitrogen, gaseous nitrogen in the gas phase. These 3 steps are relatively slower for nitrogen compared to hydrogen. Hydrogen mobility is very fast because it is a very small constituent, small element. So, its diffusivity is very fast, whether in liquid steel or in gaseous phase. So, instead of hydrogen, which is very fast, nitrogen removal is relatively slow. Moreover, oxygen, nitrogen, if they are present in liquid steel, they are surface active, so they can create problem in this denitrogenation. Why? Because the surface, at the surface of the liquid steel and the gas, there is a competition between nitrogen and surface active elements like oxygen and sulfur. If oxygen and sulfur are present in more, if their quantity is high, is present in more or higher amount in liquid steel, they will try to be accumulating more at the interface of liquid steel and gas, and then the probability of nitrogen occupying the sites will be less. So, this reaction, surface chemical reaction, will be slow. So, therefore, I had mentioned earlier, the control of oxygen and sulfur is essential in liquid steel before we can get a good removal of nitrogen. So, theoretically, though we know that nitrogen removal is possible to a great extent, but in reality, because of this kinetics, we get that about 30 to 40% only removal is possible, and this can be enhanced when we have very low amount of dissolved oxygen and sulfur in liquid steel. So, therefore, deoxidation and desulfurization, which are essential steps for having good quality, are prerequisites for degassing, particularly for nitrogen. Then I have talked about ladle furnace, how deoxidation, heating, desulfurization and adjustment of slag and chemistry of the steel, all these are possible. What is the average slag composition? About approximately 55% CO, SiO2 is much less, so the ratio is quite high. Some MgO is coming from the burnt dolomite of the in the refractory lining, and injection of argon gas to porous plug at the bottom here. There is a porous plug at the bottom, so through which argon is passed. So, this helps in bath stirring, this helps in faster removal of the inclusions from the bulk of the liquid steel to the surface and get absorbed by the slag. Then I have talked about how circulation degassing process like RH is a very popular circulation degassing process, in which way it can help degassing. So, here the rising and expanding bubbles of argon, here the argon is being sent, which forces, which pumps up the liquid steel from the ladle to this vacuum chamber, and droplets of liquid steel are formed. These droplets, because if the droplets are small, it will be easier for the nitrogen and hydrogen present in liquid steel to go to the surface and get converted to nitrogen hydrogen gas in the vacuum chamber, and vacuum helps in their faster removal. So, this RH degassing, which is a circulation degassing process, is a very useful process for bath circulation, and this argon which is being sent through one snorkel helps the liquid steel go up, get into small droplets, then come down, again this will go up. So, in this process of circulation, the degassing of hydrogen and nitrogen from the liquid steel is taken care of.